Welcome to this explainer. Okay, today we're going to decode the secret rules of how atoms interact. We're going to look past the symbols and numbers you usually see in chemistry, and instead, we're going to track an invisible cosmic tug-of-war that is happening all around us at the microscopic level. We are diving into a really fascinating concept known as ionization energy.
I mean, really think about that for a second. Why do some atoms happily give away their outer parts, while others just fiercely protect them? Well, let's start by framing the atomic world as a literal battle of strength. Right at the center of the atom, you've got a positively charged nucleus. On the outside, you have negatively charged electrons orbiting around. Because opposites attract, the nucleus is constantly pulling inward on those electrons. And honestly, the absolute strength of that grip determines everything about how that element behaves.
So, here is our roadmap for today. First, defining ionization energy. Then, the periodic table trends, putting those rules into practice, and finally, the rule-breaking anomalies. Let's get started. Section 1. Defining ionization energy. To really understand this atomic tug-of-war, we first have to figure out the exact price of stealing an electron. Essentially, ionization energy is the minimum amount of energy required to remove one single electron from an isolated gaseous atom or ion. Look, removing an electron is not something the atom does willingly. You have to force it. Because energy must always be absorbed by the atom to pull this off, the value of ionization energy is always positive. You are always paying a strict energetic price to break that invisible grip. And we actually measure this energetic transaction in kilojoules per mole. You can kind of think of kilojoules per mole as the official currency of the atomic world. This specific measurement actually dictates the fundamental reason why elements behave the way they do. Like, why metals act like metals in the first place. Let's break this down into stages, starting with the baseline cost. The first ionization energy is the minimum energy needed to remove 1 mole of electrons from an isolated gaseous atom. So it's just the energy required to pluck away that very first, most loosely held electron from the atom's grip. But what if we want to take another one? As this builds, we get to the second ionization energy. This is the minimum energy required to remove a second electron from a monovalent cation, which just means an ion that's already missing one electron. With slightly more strain in our effort, stealing a second electron requires an even harder pull. The price just went up. And scaling up the intensity even further, the third ionization energy is the energy required to remove a third electron from a divalent cation. Taking a third electron is an extreme tug-of-war against an incredibly tight grip. But why exactly does the grip keep getting tighter? Here is the absolute crucial point. The second ionization energy is pretty much always greater than the first. This escalating difficulty happens because a positively charged ion has a greater effective nuclear charge. Think about it for a sec. You've taken away an electron, but the nucleus still has the exact same number of positive protons pulling inward. With fewer electrons to share that inward pull, the nucleus just pulls back on the remaining ones with much greater nuclear attraction. It's exactly like playing tug-of-war against a team that just dropped its weakest player but kept all its strongest ones.
Section 2. The periodic table trends.
Now that we know the basic rules of the game, let's map this onto the periodic table to see exactly where the givers and the hoarders live. Elements with low ionization energy, they tend to form cations during chemical reactions. All the metals on the periodic table fall into this category. They have a low first ionization energy, meaning they easily lose their electrons. On the flip side, nonmetals have high ionization energy. They fiercely hold on to their electrons and tend to form anions instead. This simple metric perfectly explains the fundamental split of the entire periodic table.
So there are two main geographical rules that dictate the grip strength of an atom as you scan your eyes across the table. First, ionization energy generally increases as you move left to right across the same period. And second, it decreases as you move from top to bottom down a group. Let's look at the mechanics behind why this happens.
This is where the physics gets really cool. As you move across a period, electrons are being added into the exact same shell. This means you have a constant shielding effect from the inner electrons, but at the very same time, the nucleus is gaining protons. This increases the overall nuclear charge, pulling those outer electrons in much closer and decreasing the atomic size. Tighter grip, higher energy needed to steal an electron. Conversely, as you move down a group, the atomic size increases because you are adding entirely new electron shells. This drastically increases the physical distance from the nucleus to that outermost valence electron. And the further away the electron is, the weaker the nuclear attraction, making it a much easier target to steal.
Section 3. Putting rules into practice. Let's dive into a real-world scenario to test these rules and solidify what we've learned. Time for a quick mental workout. We've got 4 halogens: iodine, fluorine, bromine, and chlorine. If you had to arrange them in order of increasing first ionization energy, how would you do it? How would you rank them from the absolute easiest to steal an electron from to the absolute hardest? Take a second to picture where they sit in their group on the table.
Well, building from the bottom of the group up, the correct order is iodine, then bromine, then chlorine, and finally fluorine. Iodine basically hands its electrons over easiest, while fluorine at the very top of the group, no way, highly resistant.
And our rule holds perfectly true right here. Ionization energy decreases down the group. As we move down from fluorine to iodine, the atomic size gets larger and larger. The nucleus literally cannot hold on to those distant outermost electrons as strongly, so the energetic price to pluck one away drops significantly. Which brings us to Section 4, the rule-breaking anomalies. Because chemistry wouldn't be chemistry without a few glaring exceptions to the rules we just learned. Nature truly loves a loophole. While the general trend is that ionization energy increases across a period, there are specific points where the energy suddenly dips down when it really should be going up. If we zoom in to the hidden structural stability of electron orbitals, we find discrepancies that completely defy standard period trends. Take this really interesting anomaly between magnesium and aluminum in period 3. Aluminum is further to the right, so it should have a higher ionization energy, right? Actually, scratch that. Wrong. Magnesium is actually harder to steal an electron from. Why? Because magnesium's outer electrons are in a fully filled 3s subshell. A fully paired, filled subshell is incredibly stable. Aluminum, however, just has a single, lonely electron sitting out in its 3p subshell. That solitary electron is much less stable and much easier to pluck away. We see another major rebellion just a few steps over between phosphorus and sulfur. Sulfur is further right and should hold its electrons tighter, but phosphorus actually requires more energy to ionize. The reason? Phosphorus has a perfectly half-filled 3p orbital. In quantum mechanics, perfectly half-filled orbitals offer this hidden, protective layer of symmetrical stability.
Sulfur has a 3p4 configuration, meaning it has one paired electron among those p orbitals. That pairing creates slight repulsion, making that specific electron easier to remove than one from phosphorus's perfectly balanced.
And yep, this exact same discrepancy appears directly above them in period 2, between nitrogen and oxygen. Just like phosphorus, nitrogen features a specifically half-filled 2p3 orbital, rendering it incredibly stable. Oxygen has a 2p4 configuration, featuring a paired, filled orbital that creates a slight electron-electron repulsion. Because of that structural tension, it is actually easier to pay the energetic price to remove an electron from oxygen than from nitrogen, completely bucking the standard left-to-right period rule.
So, as we wrap up, I really want you to look at the periodic table differently from now on. It is not just some static chart hanging on a classroom wall. It's a map of a tense, ongoing battlefield of energy. The broad strokes are governed by distance and nuclear charge, sure, but the hidden quantum stability of electron orbitals allows for these totally fascinating anomalies. Keep these hidden energy battles in mind as you explore the world, because these tiny, invisible tugs of war and the elements that rebel against them are exactly what perfectly balance the chemical reactions of our entire universe. So I'll leave you with this. What microscopic tug of war do you think is happening around you right now? Keep questioning, keep exploring, and thank you